In pretty much all the molecules we've seen so far, chirality of the entire molecule came as a consequence of the presence of one or more chiral carbons. But if you think back to the origins of chirality, the basic requirement for creating a chiral object or chiral compound is not really the presence of chiral carbons. The basic requirement for chirality is our inability to superimpose an object with its mirror image. And if you recall the example of two hands or 2 feet, that was our original example of chirality. And therefore it should not be forever, since they cannot convert into each other. And to achieve such a system, we can look at systems where conformational mobility is restricted. One example of such systems are these molecules which compose of 2 phenyl rings, called biphenyls, and clearly there are no chiral centers in such molecules. You can solve the carbons are sp2 hybrid. Rotation around this single bond is free, and these phenyl rings are spinning all the time around that bond and constantly changing their relationship. However, if we start substituting that junction in these neighboring positions, for example, put bromine here and iodine here, then things start getting quite crowded. And the second phenyl ring is not able to stay in the same plane. Instead, it moves into a perpendicular plane, and so I'll use these wedges to show that. And the corresponding substituents move out of this plane. And if you look at this molecule as it is now, it lacks the plane of symmetry. And we can construct its mirror image. And I urge you to do that with the model. And what you will notice is that these 2 mirror images are not superimposable anymore. But if we ask ourselves where is the chiral carbon here, we will not find one, since these 2 molecules are basically conformers that do not interconvert. And as such, this system is chiral. Okay? All of this class of chirality is certainly observed much less frequently than the class of chirality caused by presence of chiral carbons. It is very important. And so molecules based on this structural motif, the restricted rotations in these biphenyl systems, have been used a lot to create chiral catalysts. And actually a Nobel Prize in Chemistry in the early 2000s was awarded to Professor Noyori from Japan, who worked a lot on the chemistry of chiral systems based on these conformational mobility. So chirality without chiral centers. Another broad class of chiral molecules that lacks a chiral center are the so-called allenes. And this is a very interesting exercise in hybridization. If you look at the simple molecule known as just the parent allene, it looks this way. And if you think about hybridization states of this carbon, it's sp2, this carbon is sp2, and the central carbon is sp. Now what that means is that the central carbon will have 2 p orbitals which are at 90-degree angle to each other. So while these 2 p orbitals are in plane, orbitals that connected to the other terminal carbon are out of this plane, actually perpendicular to this plane, and form a relationship like this. That now has consequences that if we put hydrogens here, they will be perpendicular to the plane of the screen this way, but in this direction they will be in the plane of the screen. As such, this molecule still has a plane of symmetry, and so it's achiral. But if we start substituting things, put a CH3 group here, and then a hydrogen here, and then hydrogen here and a CH3 group here, then what we will do effectively is introduce a twist in this molecule, because we go from planar to a plane perpendicular to the original plane. And if we construct a mirror image, and again I urge you to try this with a model, what you will notice is that these mirror images are no longer superimposable. If you flip this by 180 degrees, what you will see is that the methyl group ends up in the front and hydrogen ends up in the back, thus causing a mismatch. And again, here we see no plane of symmetry, which then causes chirality. These two are probably the most common of these less common types of chirality, and they're interesting because they combine chirality with two fundamental concepts that we already talked about. In the case of which we show under A, conformational mobility, we combine conformations with chirality, whereas in the second case we will combine the concepts of hybridization with chirality. And so this overarching principle that if we lack a plane of symmetry, if we cannot superimpose a molecule with its mirror image, it will be chiral, really has many expressions. And while we really saw only one of those expressions in detail, and that is the presence of a tetrahedral carbon with 4 different substituents, there are other types, and these two serve mostly to illustrate that point.